All right, so this last example we'll do for the subring and subfield, applying the subring and subfield test. We're going to look at rational expressions in pi. And notice I put parentheses around the pi instead of brackets. That is meaningful. And as far as this example is concerned, it means we're going to actually create a field here. So in the previous example, we run into the issue of pi not having a multiplicative inverse. It's worse. Almost all those polynomials in pi that weren't just rational numbers to begin with also don't have a multiplicative inverse. So what we do is we do something very similar to the passage from z to q. That is, we take fractions of polynomials in pi. And I'm going to put the brackets here. The brackets are polynomials in pi. And here we take what are called rational expressions in pi, but we take fractions. And the passage from z to q is also an instance of that field of fractions. And this is an instance of it. It's not relevant for the class, but just in the background, this is frac q adjoin pi. It's also actually frac z adjoin pi. Turns out if you declare that integer polynomials in pi have multiplicative inverses, which is what this does, you just get multiplicative inverses for integers. So this is not surprising. But there's this thing going on in the background taking the field of fractions, and that's what's happening here. Okay, so let's do an example with some elements here. Let's see. Something like 1 plus pi over 2 minus pi squared plus pi cubed. That's in this set. And notice that that element is not a polynomial, a single polynomial in pi. It's a quotient of them. Right? So that's what elements here look like. They look like quotients of polynomials in pi. Claim. Q adjoin pi is a subfield of C. In fact, it's even the subfield of R. And it's a very weird subfield of R. At least I think it's a weird subfield. It's not that weird, actually, from an algebra point of view. But it's not an example you might normally see when you take a course in an introductory course in fields. All right, proof. Well, 1 plus 0i is sort of like 1 over 1. And that's certainly here. We're of course applying the subfield test. So when you write your homework problems, say more than I. When you do your homework, say more than I'm saying. All right, now we need to check closed under subtraction. So let's take some p1 of pi over q1 of pi. That's one element. And some other polynomial in pi over some other polynomial in pi is another element. And we need to look at their difference. Well, how do you subtract them? Again, write in complete sentences when you do your homework. How do you subtract them? Well, you find a common denominator, right? So the common denominator is q1 of pi times q2. So we have p1 of pi, q2 of pi, minus p2 of pi, q1 of pi, over q1 of pi times q2 of pi, using standard common denominator stuff. And the numerator is a difference of products of polynomials in pi, so it's still a polynomial in pi, because polynomials in pi are a subring. And the denominator is a products of polynomials in pi, so it's still a polynomial in pi. Polynomial in pi is kind of a tongue twister for me. I feel like if I said that 10 times, it would lose its meaning. Okay, so it's closed under subtraction. Great. Nailed it. I keep forgetting my gold. Let's change this back to gold. We have 1, we're closed under subtraction, and now we need to be closed under division. So let's keep P1, Q1, P2, Q2 as before. And now we need to check closed under division. So we're going to take, P1 of pi, Q1 of pi, and we're going to divide it by P2 of pi over Q2 of pi. All right, now P1 over Q1 times P2 over Q2 inverse is just P1 of pi, Q1 of pi, times the inverse of this is clearly Q2 of pi over P2 of pi. Since it's if it's non-zero, right, it has to be non-zero for us to take the multiplicative inverse. The only way this is non-zero is if the numerator is non-zero, so this makes sense to write. And then we're just going to get P1 times Q2 over Q1 times P2, and that is products of polynomials in pi, so still polynomials in pi, and then a quotient of them. All right, so that's there too. So we're closed under division. And that completes the subfield test. So we can conclude that Q adjoined pi is a subfield of C. It's a weird subfield. It's not that weird. You've been dealing with quotients of polynomials your whole mathematical lives. This is just, instead of in an indeterminate like x or t, it's in a determinate, in particular pi. But nevertheless, that's it. It's a subfield, and that completes sort of this trio of examples. And like I said in one of the previous two, you could have replaced pi with any transcendental number, like e, or, pretty sure like cosine of 1 is transcendental. And the proof is exactly the same. Nothing is different. In a very real way that we'll see later, this last example, well, all of them are fundamental, but this last example is going to be is going to give us how do I say this without having to record the whole video? This is an important example to know how to do. And it'll show up again in sort of different guises later.